Hello and welcome to another video. In this video we're going to be working on Reconstruct Itinerary. And so in this problem you're given a list of airline tickets where tickets I represents the departure and arrival of airports from one flight. Reconstruct the itinerary in order and return it. All of the tickets belong to a man who departs from JFK, thus the itinerary must begin with JFK, and if there are multiple valid itineraries, you should return the itinerary that has the smallest lexical order. So if you have JFK LGA, that's smaller than LGB, so you should return this one first. And you may assume all tickets form at least one valid itinerary. You must use all of the tickets, once and only once. So essentially you have a airport here. You have tickets that go from starting airport to an ending airport. So if you see like MUC goes to LHR, as shown in this graph, JFK goes to MUC, shown in this graph, SFO goes to SJC, and then so on. So this graph is basically a representation of these edges. And so you want to be familiar with graphs to do this problem, but basically this represents this. And essentially what you need to do is you need to traverse every single edge, because that's a ticket. You need to start at JFK and end at wherever, I think. Yeah, you can end wherever you want, but you need to use every single edge. So in this case, if the edges are connected like this, it's pretty straightforward, right? You can only go this way. So you're doing like a depth first search, essentially, where you're just trying to go through every single edge. But in this one, it's a little trickier. So here is this again. So notice from JFK, you can go to ATL or you can go to SFO, right? So it's like, how do we know where to go? And this is the example we're going to focus on. So what we're actually going to do to help with this problem is we're actually going to sort these tickets, and that way we're always going to go to the edge that is smaller lexigraphically, and that way we're guaranteed to get our solution first. So whenever we have like from JFK as ATL and SFO, we're simply going to go to ATL first, and then if it fails, then we'll go to SFO. So we're going to sort these tickets, and we're going to build that in an adjacency list. And pretty much for every graph, you want an adjacency list or a hash map or whatever you want to call it of your node, and then all of the edges going from it, right? So it's something like we're going to have JFK, all the edges coming from JFK, and then we have ATL, all the edges coming from ATL and SFO. And this is really common in basically every graph problem that you're given a list of edges, you're going to want to rewrite it like this. So these are the keys, and then for the values, we will have an array. So let's take a look. JFK goes to SFO and ATL, but remember we're going to sort. So we're going to have ATL first, SFO. Then ATL goes to JFK and SFO. So once again, sort. And you can either build these out and then sort them, or you could just sort in the beginning, and we're going to sort in the beginning. And now SFO goes to ATL, and I believe that's it. Yeah, SFO ATL. Okay. So now we are going to look at this, and we're going to say, okay, well, we need to start at JFK, right? So in our result, we're going to have JFK. So just kind of draw that over here. We're going to have JFK in our result. We have to start there, pretty straightforward. But now where do we want to go after that, right? And so we're going to go edge by edge, and we're going to kind of like backtrack until we go through everything. And how do we know we went through everything? Well, if you look, there are 5 tickets, and there need to be 6 edges, right? So if you use up every ticket, there will always be tickets plus 1 edges, or tickets plus 1 elements in the output. So we can just check for that. Okay. So essentially, we're going to start with, okay, we're at JFK. Where are we going? We're just going to go in order. So we're going to go to ATL. We're going to put it in. We're going to say ATL is the airport we're currently at. Now we can't reuse this ticket, so we're actually going to need to pop ATL, and then we are going to, if our backtrack fails, insert it back in. So we're going to pop ATL, but we're going to go to ATL now, and then from ATL we can either go to JFK or SFO. So we're just going to take the first one always. So we're going to go to JFK. Now we went to JFK. Now we need to pop it from the ATL. So we're back to JFK. What do we have left? SFO. So we pop, then we go to SFO. Now from SFO, you can only go to ATL. So we are going to pop ATL. And now we are at ATL. And then from there, we go to SFO. And now notice that we went through every single edge. And this is kind of like an easier like this doesn't really show you the errors you run into, right? So this is a output. It's JFK ATL, JFK SFO, ATL SFO, but it doesn't really show you some problems you can run into, right? And so a problem you can run into is, let's say we're just going to make some variables like A, and it's going to go to B, and it's going to go to C. So this is like the easiest one that you can do, and C is going to go back to A. We're going to make this adjacency list again, right? So from A, and let's say we have to start at A. So from A, we have B and C. From B, we have nothing, right? We can't go back. And from C, we have A. Okay. So let's try this with this and see what happens. So we're going to start off with A as usual, because that's where we start. We have to start at A. We have to use all of these. Okay, well, let's try to go to B. So if we go to B, we cross out B, and then we go to B, and we put in B. Now we're in B, and now in B we can't go anywhere, but we still haven't really finished, right? Like we haven't used all our edges. So now we have to backtrack back. So we are going to backtrack back by getting rid of the B, and then putting B back in, and now we have to try C instead of B. So we're going to go to C this time. Cross that out, come to C. So C can go to A, so we're going to go to A. Cross that out, and now A can go to B, and now we used every edge. So now you kind of see how the backtracking works. But yeah, you have to essentially push and pop all of these, and it can get pretty expensive, right? So the time complexity of this algorithm is very difficult, in my opinion. Like worst case scenario, it's really big, and it's kind of hard to talk about. So I would just talk about like the things you're doing and like what the time complexity of all these are. We will get into that, but yeah, essentially for this solution, the time complexity worst case is pretty bad. But luckily, because of all these like optimizations with the sorting, and we start at one airport, we don't have to start at every airport, it's not as bad. And there is another way to solve this problem, but it's an algorithm that I haven't seen before. I just literally heard of today. And so I'm not even going to bother going into that one, because I think learning an algorithm for one problem, like maybe if I run into it again, or maybe in the future I'll go over it, but I don't think it's practical learning some like advanced algorithm to solve one problem that you're basically never going to use again. So this one uses things that are common to graphs, right? Making an adjacency list, iterating DFS. That's really common in interview problems, so I thought I'd go over that one. I think that's a little bit better. Okay, so now we can code it up. So first we're going to sort the tickets, right? Because we want to ensure that we go to the places that are lexicographically smaller first. Then we're going to make a flights, and we're going to say flights equals default dict. It's going to be list. Now we have to go through all the tickets. So for start, stop in tickets, we need to append the stop to the starts adjacency list, essentially. So flights start dot append stop. And the nice thing about using the default dict is if this is not in there, it will create an empty list. That's totally fine. Just makes the code faster. Okay, now we're going to start with the result, and we have to have it start with JFK. So we're going to start at JFK. Now we're going to make this backtrack function. So we're going to say def backtrack. We're going to give it an airport that we want to start at. And now we can code it up. So how do we know, once again, if we're done? So remember, our output is going to be the length of tickets plus 1. So if length of the result equals length of tickets plus 1, then we are done. So we can just return true here, and then we can return afterwards. We just want to get out of this backtrack and then return something later. So now we actually have to loop through all of our entire list, and we have to use a flight, pop that flight, backtrack, and then if it fails, we have to put it back in. And we're going to use enumerate here, and we can't actually pop in place because we are going to pop, or sorry, yeah, we're going to pop, and then we are actually going to push it back in before we have a problem, essentially. So let's do that. So we are going to say res.append. We're going to pop something. So we need to have the loop first of all. I forgot about that. So we need to have a loop, so we can just say for I index and then like v in enumerate. You can use better value names if you want to. And then this is going to be flights for the current airport we are at. I guess maybe instead of v, we can call it next airport. That would make sense. So next airport, res append next airport, whatever we chose. Now we need to get rid of it from the adjacency list because we can't reuse the ticket. So we can just delete. We don't need the pop because we don't need the value. We already got it. So now we are going to delete it. So we're going to say delete flights airport I, delete that index, right? Now we are going to check if the backtrack returns true. So if the backtrack returns true, then we can just return. We don't want to be redoing this because that means we found our solution. So if backtrack return true, that. Otherwise, we need to actually fix everything we did. So we're going to pop from the result, and we are going to add back into it, right? And so that's what we need to do. So we're going to say flights airport insert I next airport. Essentially, this is also not inefficient, or this is also not efficient because we're pushing back into like the middle of an array, which is not great, but we have to maintain the order, so there's not really much we can do about that, I don't think. Unless, like I said, we use the more complicated algorithm that you've literally never seen before and only use for one problem. So, okay. So now, if we went through this whole loop and everything failed, we can just return false because we failed. Otherwise, now we can actually call our function. So we can call backtrack, and we want it to start at JFK. And then we can return the result. So let's see what happens there. It's actually a little bigger. Okay. I did mean tickets. So you could see it's still pretty efficient, but it's just not as good as the other one, but it's still not bad. But worst case scenario, like I said, this is really bad. Because if we take a look at it, and like I said, I don't know if I can calculate the time exactly, but we can just go over everything. So for the time, so if you think about it, for a backtrack, we are going through every single edge connected to some node, which could be worst case, you know, like all of the edges. So that's like E every time. And now there is going to be like one less edge every time, right? But worst case scenario, it's something like E factorial. Because essentially, if you have like 300, or close to 300, it essentially, you know, it's going to be roughly the same every time. So if you have a ton of edges and you go to like, actually, I don't know if you can go to yourself. Maybe you can. I think you can. Like, I think you can have self loops. Yeah, I don't see it saying you can't. So if you have a bunch of like self loops, you know, it's kind of hard to figure out what to go to, and there might be some like optimization there, I guess, but either way, you're still like going through all it all. So it's definitely not great. I think there might be an optimization here though that we can probably do. I guess we could do, yeah. So let's do that, I guess, right? We can use an optimization. So if we, let's say we went to an airport and like if we go from JFK to JFK and that didn't work, then it has a bunch more JFKs right after it. We don't need to go to the other one. So we can do that, I guess. So let's do that. So we can say if I is greater than 0 and next airport equals flights I minus 1. Right, if it's the same one and we already tried it, I think we can continue. So that is a slight optimization. So let's see if that works. I think it should. Yeah. So like on average, it should be an optimization. You know, it runs different times, but yeah. But either way, even if you can't go to yourself, you can still go to other ones. So I don't know the exact like time here, but it's going to be really bad because essentially for every edge, you can go to, you know, maximum edges, more edges. So like for every edge, you have E options, and then for the next edge, you have E options and so on, right? So it's like E to the, you know, E times E times E times E times E. E will go down by like 1 every time when you pick an edge, but it's still really bad. So yeah, it's not the best. And also we are doing this inserting in place. So like I said, this is like really complicated what the exact time complexity is, but I think it's really bad. But I would just talk about these things with the interviewer. For backtracking, the exact time complexity, it's kind of hard to calculate for sure. Like there's a lot of stuff there. So for the space, that one should be more straightforward. And essentially, if you think about it, so you have this default dict. So it will just have nodes and then a list of edges, a list of nodes that it is connected to. So that's usually something like v plus e, right? Because you're storing every single node and then every single edge from there. So that's roughly v plus e. Maybe you can argue like whatever the max is of v and e, somewhere along those sorts, right? And then for the rest of it, we're not really storing anything. So that's something like this. And yeah, I think that's going to be it for this problem. Like I said, time complexity hard to figure out for a backtracking problem, especially like this. So if anyone has any thoughts of something clearer, I would love to hear about it. But as far as this problem, I think the only tricky thing about this solution, honestly, that I found is you can just see, like, once you understand time complexity, you can see, like, wow, worst case, it's really bad. So you might actually just, like, not even consider this one because you might think, like, it might be too slow. Where you could still, it still is okay because of, like, the optimizations and the sorting and stuff. But, yeah, worst case, I would still think it would be, like, pretty bad. So yeah, that's going to be all for this problem though, so hopefully you liked it, and if you did, please like the video and subscribe to the channel. And I will see you in the next one. Thanks for watching.